Hi, I'm Roberto Parisella, and I want to talk about the work we did with Michele Ciampi and Daniele Venturi, described in the paper on adaptive security of delayed input Sigma protocols and Fiat Shamir NIZKs. A Sigma protocol is a three-round proof of knowledge for a language associated to a relation. An algorithm called prover on input a pair statement witness, compute a first message A, and send it to another algorithm called verifier, which samples a random seed and sends it back to the prover as the second message, which is also called challenge. Then the prover sends back the third message, Z, and at the end of the interaction, the verifier, having on input only the statement X, but not the witness, has to check if the set of messages or transcript satisfies some conditions, and then output 0 for reject or 1 for accept. We can also define this protocol in the CRS models, which means we suppose the existence of a trusted third party that computes a common reference string, CRS, and makes it available to both the prover and the verifier. Our work is based on the outstanding breakthrough of Canetti, Lombardi, and Weeks. They consider a special class of Sigma protocol called trapdoor Sigma protocol, which means that in some way we can compute a challenge to prove a false statement. We will explain it in detail later. Their work is based on the Fiat-Shamir transform, which I briefly recall here. As we can see in the slide, the Fiat-Shamir transform is a way to obtain a non-interactive zero-knowledge proof, or NIZK, from a Sigma protocol. We let the prover computing the challenge using a cryptographic hash function, and so the challenge C will be the hash of the first message A. And then it sends the whole transcript to the verifier, which has to check if it received the valid transcript and if the challenge is the hash of the first message A. Due to a famous impossibility result, Fiat-Shamir transform is unconditionally secure only in the random oracle. However, Canetti, Lombardi, and Weeks recently proved that if we start from a family of cryptographic hash functions called correlation intractable hash functions, and if the starting Sigma protocol is a trapdoor Sigma protocol, then Fiat-Shamir transform is secure in the standard model. However, this left us with two important open questions. The first is about the trapdoorness property of a Sigma protocol. And particularly, we would like a compiler to define a trapdoor Sigma protocol from any Sigma protocol. The second open question is about how to reach either adaptive non-interactive soundness or adaptive input non-interactive zero knowledge with this framework. Actually, we already knew that if we apply this framework to the famous Lepid-Shamir Sigma protocol for a Hamiltonian graph, we obtain a NIZK that enjoys this definition of adaptive security. So in principle, we could use NP reduction and obtain this kind of security for all NP languages. However, NP reduction are very expensive objects. So in this work, we show how to define NIZK with adaptive security using this framework without the needs of NP reduction. The stronger definition of security for NIZK are defined in the following way. In the slide, we can see how adaptive non-interactive soundness is defined by the fact that each malicious probabilistic polynomial time attacher that can try to forge a valid proof for a false statement has negligible probability to convince a verifier, even if it is allowed to choose the statement adaptively after seeing the CRS. And here we can see how the adaptive input non-interactive zero knowledge is defined. The idea is that there exists a simulator split into phases S1 and S2. The first phase has to compute a CRS, and the second phase is having on input a statement has to compute a valid proof. And moreover, the procedure has to be indistinguishable from an honest interaction of the protocol. So let's summarize our results. The first is about adaptive non-interactive soundness. And we notice it that if we apply Fiat Shamir transform with correlation intractable hash functions to traptor sigma protocol, but we compute the challenge hashing the statement concatenated to the first message A, we define a NIZK that enjoys a directly adaptive non-interactive soundness. On the other hand, instantiated this framework with the classic Fiat Shamir, so letting the prover compute the challenge hashing only the first message. If the starting sigma protocol is a traptor sigma protocol that also enjoys this additional property called adaptive input honest verifier zero knowledge, we obtain a NIZK with non-adaptive soundness, but with adaptive input non-interactive zero knowledge. The third and the most technical of our results is a general compiler that, under the DDH assumption, adds this property of adaptive input honest verifier zero knowledge to any sigma protocol for which this definition makes sense, which is the class of all the layered input sigma protocol that I'll briefly, formal describe later. Then we define the compiler that add traptorness to any sigma protocol using as additional tool a perfect correctness public key encryption scheme. However, this compiler doesn't preserve the delayed input property. The last result is a compiler that adds adaptive input honest verifier zero knowledge to any delayed input sigma protocol, preserving the traptorness property. And to define this compiler, we also defined a new commitment scheme called extractable IDTC. Now I can show in details most of our results. Let's start with the compiler that had adaptive input honest verifier zero knowledge. As I said, we want to deal with sigma protocol that is delayed input, which means that the first message A is independent from the pair statement witness. Formally, we require that this pair is makes available to the prover only in the third round. For this protocol, makes sense to define stronger notion of security, and one of them is this adaptive input honest verifier zero knowledge, which is defined by the existence of a two-phases simulator. The first one, having on input only the challenge C, has to compute a first message A, and then the second one, receiving as additional input the statement X, has to compute the third message Z, such that ACZ is a valid transcript. Also, for our compiler, we need a commitment scheme called instance-dependent traptor commitment, or IDTC, which is a commitment scheme associated to a language L. There is a commitment algorithm that takes an input the message to commit A and an element X, and output a valid pair of commitment and the commitment. Moreover, if the commitment is if X is not in L, then the commitment is bind, in the classical sense that for each X not in L and commitment, there exists at most one message A for which it is possible to compute a valid commitment. Instead, if X is in L and we have a witness for that, we can compute a valid commitment from each pair of commitment and first message. And we already knew that if there exists a sigma protocol for the language L, then there exists an IDTC associated to the language L. So for our compiler, we used an IDTC for the language of DH tuples and a sigma protocol to prove that a given tuple is a one non-DH tuple, which is a specific kind of non-DH tuple. The idea, as we can see in the figure, is that the prover compute the first message A, but it would send it only in the third round. Instead, it picks an arbitrary tuple T in one non-DH, and it uses the commitment algorithm to compute a valid pair of commitment and the commitment for the first message A under the tuple T. Now T is not a DH tuple, so the commitment is bound to the message A. And then we can expose the tuple and the commitment at first and send the original first message and validate the commitment in the third round. In parallel, to prevent the fact that the malicious prover could use a DH tuple and expose a commitment which is not bound to any specific first message A, we run a Sigma protocol to prove that the tuple T is a one-on-DH tuple. The verifier then has only to check if it received a valid transcript ACZ for the original protocol, if it receives a valid transcript A to the one-on-DH, Z to the one-on-DH for the one-on-DH protocol under the statement T, and it has to check the validity of the opening for the commitment scheme. And here it is how the simulator is defined. The idea is that we can use here a tuple, which is a DH tuple, to expose a commitment which is not bound to any specific first message A. And we do it in the first phase, and then we use the zero-knowledge simulator of the one-on-DH protocol and expose a valid first message. Then in the second phase, we have the statement X, and we can compute a valid first and the third message AZ. And then, exploiting the trapdoorness property of the IDTC, we can compute a valid commitment for the message A we have just computed, and the commitment we have exposed it before. It's important to note that the security is only computational since it relies on the DDH assumption. Let's now move on to the NIZK-related results. First, I define a little bit more formally what Canetti, Lombardi, and Weeks did. A family of city-dash function is said to be correlation intractable with respect to an ensemble of relation if given a seed K and a relation. It's hard to find an X such that X, H, KX is in the relation. And moreover, a relation is sparse if the probability to uniformly sample couple in the relation is negligible. We knew that there exists a family of correlation intractable hash function for all sufficiently sparse sigma protocol. For all, sparse relations. We want to deal with sigma protocol with this property. For every CRS, false statement X and first message A, there exists at most one challenge E, for which it is possible to compute a valid third message Z. And then this function that associates the triple of CRS, false statement and first message, to the unique bad challenge is well defined and is called the bad challenge function. We note that even if it's well defined, in general it is not efficiently computable. Such sigma protocols are trapdoors if there exists a pair of probabilistic polynomial time algorithm trapgen and bad challenge, such that trapgen compute a CRS along with the trapdoor, computationally indistinguishable from an honest generated one, and bad challenge using the trapdoor of the CRS to efficiently compute the bad challenge function. So, from Canetti, Lombardi, and Weeks' works, we know that instantiated the Fiat Shamir transform with correlation intractable hash functions, and starting from a trapdoor sigma protocol, we obtain a sound NIZK. On the top of that, we proved that if the starting sigma protocol is a delayed input sigma protocol that also enjoys this adaptive input honest verifier zero knowledge property, we define a sound NIZK that enjoys also adaptive input no interactive zero knowledge. We have only to show how this two phases no interactive simulator is defined. And we define it using only the two phases honest verifier zero knowledge simulator and the programmable property of the hash functions. Particularly, in the first phase S1, we sample an honest CRS, we pick an arbitrary C as the challenge, we compute the first message A using the first phase of the honest verifier zero knowledge simulator, and then we compute a seed K such that HKA is equal to C. This is possible through the programmable property of the hash function, and we output the CRS. In the second phase, we have received the statement X, so we just use the second phase of the honest verifier zero knowledge simulator, and we output the valid transcript. Moving on, I'll show how we define a compiler to add the disruptorness property to any Sigma protocol. Well, first of all, it's not really any Sigma protocol, but is on the Sigma protocol for which this property makes sense. So there has to be, as we said, a well-defined batch challenge function that associates each triple of CRS, false statement X, and first message A to its unique batch challenge. Using a public key encryption scheme and restricted the challenge space to 0,1, we have defined this compiler. The idea is to add a public key to the CRS, and then the prover, once computed the first message A, computes on also the two possible third messages, zeta with 0 and zeta with 1, relative to challenges 0 and 1. Then it uses the public key in the CRS to encrypt those messages and send the first message A and the two ciphertexts as the actual first message. In the third round, upon received the challenge C, it sends the corresponding third message zeta with C with the randomness it used to encrypt it. The verifier is just to check if it received a valid transcript, and if the ciphertext it received in the first phase is well formed. TrapGen algorithm is the same as the honest setup algorithm, except that it samples the corresponding secret key as the trapdoor, and the batch challenge algorithm uses this secret key to recover the two possible third messages zeta with 0 and zeta with 1 from the ciphertext. Then using the verifier algorithm to check if one of them leads to a valid transcript, and eventually output the challenge of the valid transcript. Since the starting Sigma protocol has a well-defined challenge function, for a false statement, it cannot happen that both zeta with 0 and zeta with 1 leads to valid transcript, and this shows the correctness of this batch challenge algorithm. Now, in principle, we know many efficient delayed input Sigma protocol with a well-defined challenge functions, such as all Sigma protocols defined by Maurer by one-way homomorphisms. However, we would like to use our two compilers in cascade and have this nice Fiat Shamir NIZK with adaptive input non-interactive zero knowledge. For example, we want to apply the compiler for trapdoorness and the compiler for adaptive input zero knowledge and the Fiat Shamir transform. However, we can do that. And the reason is that the trapdoor protocol defined by our first compiler is inherently not a delayed input Sigma protocol, since it needs the pair statement witness to compute the third messages from the beginning. It is also not clear if we can use the compiler for trapdoor, or if the first compiler even preserves the trapdoorness property at all. And the reason is that the batch challenge algorithm takes the first message A as its input, but our protocol defined by the compiler for adaptive input honest verifier zero knowledge actually send the original first message A only in the third round. And so to partially overcome these problems, we defined a new compiler that adds the adaptive honest verifier zero knowledge property to any delayed input Sigma protocol, but also preserving the trapdoorness property. We did that through a new commitment scheme called extractable IDTC, which is an IDTC defined directly in the CRS model. So we require the existence of a setup algorithm. We require the fact that the commitment algorithm takes as additional input a CRS omega. The binding and the trapdoorness property are the same. And then we require the existence of an extractor algorithm that on input a pair CRS trapdoor, an X which is not in R, and a commitment, compute the first message A bound to the commitment. And the compiler is exactly the same, is defined exactly in the same way as the one with non-extractable IDTC. So we already know that the construction yields a sigma protocol with adaptive honest verified zero knowledge. We just need to check that trapdoorness is preserved. And in our works, we show that from the fact that the original sigma protocol is trapdoor, so also has a well-defined challenge function, from the property of the structural algorithm of the IDTC, and from the fact that we know one protocol to prove that the tuple T is a 1 on the H tuple, which is also a native trapdoor sigma protocol. We were able to prove that the trapdoorness property is preserved. So, summing up our results. On one hand, starting from a sigma protocol just with a well-defined challenge function, we can add the trapdoorness property. We can run the Fiat-Shamir transform, hashing the statement X concatenated to the first message A, and we define a NIZK that enjoys adaptive non-interactive soundness. On the other hand, if we start from a delayed input trapdoor sigma protocol, we can add the adaptive input honest verified zero knowledge property, preserving the trapdoorness property. We can run the standard Fiat-Shamir transform, computing the challenge C, hashing only the first message A, which is now independent from the statement, and we define a NIZK with non-adaptive soundness, but adaptive input, non-interactive zero knowledge. And once again, I stress the fact that we did that without the need of expensive NP reduction. However, it's still an open question how to define NIZK through these frameworks that enjoys both adaptive non-interactive soundness and adaptive non-interactive zero knowledge without the needs of NP reduction and for efficient sigma protocols. Thanks for your attention.